Welcome back to the channel. Today, we're diving into one of the most fundamental concepts in AI and machine learning, vectors and embeddings. If you've ever wondered how computers understand words, images, or even your preferences on Netflix, you're in the right place. By the end of this video, you'll understand exactly what vectors and embeddings are, why they're everywhere in AI, and how you can start using them yourself. So let's jump right in. Let's start with the basics. A vector is simply a list of numbers that represents something in a mathematical space. Think of it like coordinates on a map. In 2D space, a vector might be 3, 4, meaning 3 steps right, 4 steps up. But vectors can have any number of dimensions. While we can easily visualize 2D and 3D vectors, in AI, we often work with vectors that have hundreds or thousands of dimensions. A 300-dimensional vector would be a list of 300 numbers. Here's what a simple vector looks like in Python. Simple, right? Just a list of numbers. But here's where it gets interesting. An embedding is a special type of vector that represents real-world objects, like words, images, or even your preferences on Netflix, in a mathematical space where similar things are close together. Imagine we could take every word in English and plot them on a map. Similar words would cluster together. All animal words in one area, all vehicle words in another. That's exactly what embeddings do, but in hundreds of dimensions instead of just 2. The embedding process converts raw data into these meaningful numerical representations that capture semantic relationships and patterns. Here's the thing. Computers don't naturally understand words, images, or concepts. They only understand numbers. Embeddings are the bridge that translates human concepts into computer language. Without embeddings, dog and puppy are completely different to a computer. With embeddings, the computer can see they're related. Embeddings give us 3 superpowers. First, semantic similarity. Related concepts have similar vectors. Second, mathematical operations. We can do math with meanings. Third, dimensionality reduction. We can compress complex data while keeping the important relationships. There are several types of embeddings, each designed for different kinds of data. Let's explore the main ones. Word embeddings, like word2vec and glove, convert words into vectors. The famous example, king minus man plus woman equals queen. Sentence embeddings, like Bert and sentence Bert, capture the meaning of entire sentences or documents. Image embeddings convert pictures into vectors that capture visual features and similarities. Models like ResNet and Clip can understand that a photo of a golden retriever is similar to other dog images. Let's make this concrete with the Netflix recommendation example. How does Netflix know what movies you might like? Netflix creates embeddings for both users and movies. Your user embedding captures your preferences, while movie embeddings capture genres, themes, and characteristics. When you rate a movie highly, your embedding moves closer to that movie's embedding in the vector space. To recommend new movies, Netflix finds movies with embeddings similar to yours that you haven't watched yet. Embeddings are everywhere in modern AI applications. Let me show you where you encounter them daily. When you search Google, embeddings help understand that searching for car repair should also show results about auto maintenance and vehicle fixing. Instagram uses embeddings to understand image content for better recommendations. Amazon uses them to suggest products and understand reviews. ChatGPT and other AI assistants use embeddings to understand context and generate relevant responses. They're also used in translation, sentiment analysis, and content moderation. Creating embeddings involves training neural networks to learn meaningful representations from data. Let me show you the process. The easiest way is using pre-trained models. Here's how to create embeddings for text. For specialized domains, you might train custom embeddings. For production applications, you'll want to store embeddings in vector databases like Pinecone, Weaviate, or Chroma for fast similarity search. Once you have embeddings, how do you measure how similar they are? There are several distance metrics, but cosine similarity is most common. Cosine similarity measures the angle between vectors, not their length. It ranges from -1 to +1, where 1 means identical and -1 means opposite. Other metrics include Euclidean distance, Manhattan distance, and dot product. Each has different use cases. Here's how to find the most similar items in a collection. Embeddings are powerful, but they're not perfect. Let's talk about important limitations you should know about. Embeddings can inherit biases from training data. Historical biases in text can lead to unfair associations in the embedding space. For example, if training data associates programmer more with male than female, the embeddings will reflect this bias. Traditional embeddings struggle with words that have multiple meanings. Bank could mean a financial institution or the side of a river. Modern contextual models like BERT help, but it's still a challenge. High-dimensional embeddings require significant storage and computation. 1 million documents with 768 dimensional embeddings need about 3 gigabytes of storage. Consider the trade-offs between embedding quality and computational resources. Let's recap what we've learned today. Vectors are a list of numbers that represent data in mathematical space. Embeddings are special vectors that capture semantic meaning and relationships. They're the foundation of modern AI, powering everything from search engines to recommendation systems to language models. You now have the foundation to start working with embeddings in your own projects. The code examples I showed are all available in the description below. If this video helped you understand embeddings, smash that like button and subscribe for more AI tutorials. What would you like to learn about next? Let me know in the comments. Thanks for watching, and I'll see you in the next video.